Welcome to the Deep Dive. Tonight, we're looking at a story many of us think we know, the sinking of the RMS Titanic, April 14th, 15th, 1912.
A truly iconic moment in history, but it's often simplified.
That's what we want to dig into. For over a century, the focus has been, the iceberg. But was it just that? Or, well, something much bigger?
Over 1,500 people lost their lives.
And we're asking tonight, was it purely bad luck, wrong place, wrong time, or a whole chain of events?
Exactly. The iceberg is, well, it's the obvious smoking gun, isn't it? But when you really dive deep, you find this disturbing convergence of factors.
Like what?
Decisions made way up high, the actual materials used to build the ship, even, the specific weather and sea conditions that night, they all played a part.
Okay, so to unpack all of this, we're going to use a couple of tools. You mentioned the Ishikawa fishbone diagram.
Yeah, it's a great way to visualize the different categories of causes, help sort things out.
And also the 5 whys.
Right. Just keep asking why to drill down past the surface symptoms to the real root causes.
So our mission for you, listening, is pretty clear. We want to see how 6 key areas, let's list them: methods, materials, people, machine, measurement, and environment, how they all fed into the sinking of this supposedly unsinkable ship.
We're looking for those hidden fractures, the weaknesses beneath the headline story.
It's about seeing how lots of smaller, maybe seemingly separate issues can line up to cause a total catastrophe.
That's it, precisely. The domino effect.
Okay, let's start with methods. This is about procedures, right? Decisions made during the voyage.
Operational stuff, yeah.
And the big one seems to be speed. The Titanic was going fast, 22 knots, in an area they knew had icebergs. Why? Why push it so hard?
Well, the pressure to stick to the schedule was just immense. Really huge.
For Captain Smith or the company?
Both, really. Captain Smith, the White Star Line executives, arriving in New York on time was a massive deal for them.
Not just keeping passengers happy.
Oh, much more than that. It was marketing. It was prestige. This is a really cutthroat business, the transatlantic route.
Right, so being late wasn't just inconvenient.
No. It hit their reputation. It hit the bottom line. Speed, reliability. Those were the big selling points in that era. It was all very glamorous, very competitive.
Still, you'd think ice warnings might make them ease off a bit. Why prioritize speed that much?
It ties into the culture of the time, I think. Early 20th century maritime thinking often linked speed directly with, progress, pushing boundaries.
A bit of bravado involved.
Definitely. Taking risks was almost seen as part of innovation. These fast crossings were a statement.
And then there's the whole unsinkable reputation.
Yeah.
That must have factored in, made them feel invulnerable.
Oh, absolutely. That idea that the ship was practically indestructible.
Which was pushed hard by the builders, by the press.
It almost certainly created this dangerous sense of complacency. Why would you slow down dramatically or, swerve hard if you genuinely believed your ship couldn't really sink?
Nobody wanted to challenge the myth.
It seems that way. And that's a critical point, isn't it? How a really powerful marketing message, that unsinkable tag, actually ended up undermining basic safety thinking.
So you've got this culture of speed, this almost blind faith in the ship's design. Caution just went out the window.
It feels like it took a backseat, yeah. And look at their actual procedures. They got multiple wireless ice warnings during the day.
But didn't change course.
No formal change, of course, to avoid the known ice fields. That's, well, it's significant.
Wow. And the lifeboat drills.
Pretty inadequate by all accounts. Just 2 quick drills in 3 days, and apparently lots of passengers didn't even take part.
So wrapping up methods, it's not just one single bad decision.
No, it's a mix. Corporate pressure, that false sense of security we talked about, and just not having strong enough safety rules for the dangers they actually knew were out there.
A culture where bravado and promotion maybe mattered more than caution?
That sums it up well. A system where taking risks felt normal, and maybe the drive for prestige overshadowed some fundamental safety needs.
Okay, let's shift gears. Let's talk about materials. The actual physical stuff that Titanic was built from. We know the hull plates buckled, rivets popped. Why did it fail so badly on impact?
Yeah, the investigations afterwards found some pretty serious issues. The rivets, for instance, especially the ones used in the bow section.
What was wrong with them?
They had a really high level of slag, which is basically impurities left over from making them. Too much slag makes the metal brittle.
Brittle rivets holding the ship together. Why?
It looks like it came down to rushing the job and, frankly, cutting costs. To meet the deadlines, they seem to have used rivets with more slag. A pretty shocking trade-off when you think about it.
Cutting corners on rivets. Who made that call?
Well, Harland and Wolff, the builders, were under enormous pressure from White Star Line. Get it built, get it sailing. So evidence suggests they used some lower-grade iron batches for rivets, maybe thinking those parts of the hull, the bow especially, wouldn't be under as much stress.
Weren't there tests? Standards to stop this sort of thing?
Not like today. Back then, maritime metallurgy, the science of metals for ships, it didn't have the kind of standardized tests we rely on now, especially not for how materials behave in extreme cold and under sudden impact.
So regulators just trusted the builders?
Largely, yes. There was a lot of faith put in the reputation of big firms like Harland and Wolff. People assumed they had their own high standards.
Plus the unsinkable thing again?
Probably played a part. Why look too closely at the nuts and bolts or rivets, in this case, if the whole thing is supposed to be indestructible anyway? It points to this dangerous over-reliance on reputation instead of, independent checks.
So those profit motives, the rush to finish, might have directly compromised safety.
It certainly looks that way. And it wasn't just the rivets either. The steel plates themselves had an issue.
What with that?
Their ductile brittle transition point. Basically, the temperature at which the steel goes from being somewhat flexible or ductile to being brittle and likely to fracture. That point, for the Titanic steel, was actually above the freezing temperatures of the North Atlantic water that night.
So in that icy water.
The steel became stiff, brittle. Instead of maybe bending or denting on impact, it was more likely to crack and fracture. So the hull, which should have been this strong barrier, became much more fragile in the cold. Turned it into a sieve, as you said earlier.
So the supposedly mighty hull had this hidden weakness, triggered by the exact conditions it faced.
That's the surprising and tragic reality, yes.
All right, let's move to people, human factors. Clearly crucial here. The lookouts, first start reports, say they didn't have binoculars. How could that happen?
It's one of those details that sounds almost unbelievable, doesn't it? But it seems the second officer, David Blair, had the key for the locker where the binoculars were kept.
Okay.
But he was reassigned right before the ship sailed, a last-minute crew shuffle. And in the handover, or lack thereof, the key didn't get passed on.
And there wasn't a spare.
Apparently not readily available. So you have a personnel change, a missing key, no backup plan. And the lookouts are left scanning the horizon with just their eyes.
For something as vital as binoculars. Why no spare, no check?
Again, it probably comes back to that sense of complacency we keep mentioning. Standard checklists back then. They likely didn't include double-checking that critical gear like binoculars was actually accessible. The assumption might have been. It's on the inventory list, so it's fine.
A failure to check the basics.
A systemic failure, yeah. Driven by that underlying belief.
In the ship being unsinkable.
Exactly. If you believe you're invincible, maybe checking for the binocular key seems less critical. It's strange how the marketing hype might have trickled down to affect even these fundamental operational details.
The ship's reputation creating blind spots. And you mentioned the rigid hierarchy. How did that play in?
Well, the maritime world then was very hierarchical, very strict chain of command. Junior crew might have been hesitant, to question superiors or point out potential problems like missing equipment.
Discouraged speaking up.
It could certainly stifle the flow of important information upwards, potentially hindering checks on risks.
Beyond the lookouts and the binoculars, what other human elements were critical?
The handling of those ice warnings is definitely another one. We know multiple warnings came in via the wireless room.
But
they were hand-delivered to the bridge, yes, but they weren't formally plotted on a hazard chart. They didn't become part of the immediate navigational picture in the way they should have.
So the information was there, but not really used effectively.
Precisely. And then, as we touched on before, the lifeboat training, just not thorough enough. Which explains, tragically, why so many boats were launched half-empty.
Communication breakdowns, inadequate training.
It all amplified the technical problems, yes.
So if you trace it back,
Yeah.
overconfidence leads to poor preparation.
Yeah.
Bad communication means warnings are missed. Poor training makes the emergency worse. It's a grim picture of human error compounding risk.
Exactly right. And if you follow the why for each of these, you often end up back at that same place. This pervasive overconfidence, this lack of questioning the way things were done.
Okay, let's look at the machine itself, the engineering. Titanic was a marvel, but let's talk specifics. Watertight bulkheads designed to contain floods, right? But they didn't go all the way up.
That's right. They only extended up to E-deck. The design was based on what they thought were likely accident scenarios, like a head-on collision where maybe one or two compartments would flood.
So contain the damage locally.
Exactly. And for that kind of limited breach, bulkheads up to E-deck would probably have worked, but they didn't really design for a long, glancing blow like the iceberg delivered.
Which breached multiple compartments along the side.
Correct. And once about 6 compartments were breached, the bow dipped low enough for the water in those flooded compartments to simply spill over the tops of the bulkheads into the next ones.
Like water overflowing an ice cube tray.
A very good analogy. The system was bypassed because the type of damage was different from what the designers had prioritized.
Why were their assumptions about damage so limited? Why not plan for worse?
Well, they didn't have a lot of real-world data on massive collisions involving these huge new liners and simulation technology. Very basic compared to now.
So it was based more on past experience than future possibilities.
Engineering back then relied a lot on practical experience, rules of thumb, precedent, not the kind of complex computer modeling we do today.
A gap between the design theory and the messy reality of the ocean. What about oversight? Did regulators check these designs?
Interestingly, no, not in the way we'd expect today. Shipbuilding companies were largely allowed to self-certify their designs.
They marked their own homework.
In a sense, yes. There was a huge amount of trust placed in the industry's own expertise. It really took the Titanic disaster to show everyone that self-regulation wasn't enough. That led to major changes in maritime safety rules.
A hard, tragic lesson about trusting industry without independent checks. Okay, what about the bilge pumps? Could they have helped?
Sadly, no, not in this situation. Their total capacity was around 1,700 tons of water per hour.
Which sounds like a lot.
It does, but the estimates are that water was flooding in at something like 25,000 tons per hour after hitting the iceberg. Maybe more.
So completely overwhelmed.
Utterly. They didn't stand a chance. And there wasn't enough redundancy either, not enough backup pumping capacity if the main ones couldn't cope or failed.
So even with advanced engineering for the time, the ship had these critical vulnerabilities when faced with that specific damage.
Exactly. The watertight compartments weren't high enough, the pumps weren't powerful enough for that scale of breach. Once the damage was done, sinking was, tragically, almost inevitable.
Now let's turn to measurement, gathering and using data, specifically those ice warnings again. We know the Marconi wireless room got them. Why didn't they get to the right people or have the right impact?
This really highlights how new technology was understood or misunderstood back then. Wireless was revolutionary, yes, but it was seen mostly as a perk for passengers.
Sending telegrams back home.
Exactly. Sending personal messages, business notes. It wasn't primarily viewed as a critical navigational safety tool yet.
So a life-saving technology treated almost like an onboard luxury.
That seems to be the case initially. The early marketing, the way it was used, focused on that person-to-person communication aspect, integrating it fully into the rigorous minute-by-minute procedures of bridge navigation and safety protocols. That took time. It lagged behind the technology itself.
Were there no rules then?
Yeah.
No regulations saying, if you get an ice warning, you must tell the captain immediately?
Not in a formal, internationally agreed way that mandated how it fit into navigation. The UK Board of Trade had some regulations in 1906, I think, but they hadn't really kept pace with how fast Marconi's wireless was spreading and changing things.
So the rules were lagging behind the tech.
That's a great way to put it. Governments, maybe not fully grasping the safety potential of wireless yet, were slow to create the frameworks needed. So the result was critical data about ice was received.
But it stayed in the wireless room log.
Or wasn't given the urgent priority it needed. There wasn't a robust, mandatory process for analyzing that hazard info and ensuring it directly influenced the ship's course and speed. The data existed, but the system to use it effectively didn't.
Okay, last category. Environment.
Mm-hmm.
The conditions on the night itself. It wasn't just that there was ice, was it? Other factors were at play.
Definitely not just the ice. A whole set of unusual environmental factors came together to make things much, much worse.
Like what?
Firstly, it was incredibly dark. No moon at all that night because of the lunar cycle.
Pitch black.
Pitch black. And secondly, the sea was exceptionally calm. Like a mill pond, descriptions say. Mirror flat.
Which sounds nice, but was actually bad.
Very bad. Normally, even small waves would break against the base of an iceberg, creating a line of white foam that lookouts could spot from a distance. On a flat, calm sea, that visual cue is gone. The iceberg just blends into the darkness.
Wow. So the calm sea actually hid the danger. You mentioned something about a temperature inversion, too.
Yes. Atmospheric conditions created a slight temperature inversion, which can cause optical effects. In this case, it might have created a bit of a mirage, potentially making the horizon seem slightly higher than it was.
Making it even harder to spot something low on the water, like an iceberg.
Exactly. It could have further masked the iceberg's silhouette against that already dark, flat sea.
Were sailors back then aware of these kinds of, well, optical tricks and the danger of calm seas near ice?
Not really, not in the way we understand them now. Nautical training back then didn't cover these polar optical phenomena in much detail, and these big commercial liner routes across the North Atlantic were still relatively new territory for many officers. They wouldn't necessarily have had lots of experience with these specific, subtle Arctic conditions.
So these unusual, poorly understood conditions basically stole their reaction time.
That's the crux of it. The lack of moonlight, the dead calm sea removing wave breaks, the potential mirage effect. They all conspired to remove the visual cues that might, just might, have given the lookouts a few more crucial seconds. A perfect storm of bad environmental luck.
Okay, looking back across all 6 areas, methods, materials, people, machine, measurement, environment, it's overwhelming how interconnected it all was. If you had to boil it down, what's the single biggest root cause tying it all together?
You know, synthesizing all of this, the one theme that just keeps coming up again and again is that pervasive cultural belief in the Titanic's invulnerability.
The unsinkable myth.
It wasn't just marketing fluff. It seems to have genuinely permeated the thinking. It affected decisions about speed, about safety drills, maybe even about the quality control of materials, the need for backup systems, how seriously warnings were taken.
So all those 5 whys we talked about, they kind of lead back to this central point, this feeling of being untouchable.
I really think so. If there'd been more humility, maybe a greater respect for the sea's power, for the possibility of failure. If assumptions had been challenged more strongly in any one of these areas, maybe things turn out differently.
Instead, weakness is just cascaded.
Exactly. The lack of good lifeboat drills mattered more because they were going so fast. The brittle rivets made the impact far worse than it might have been. The missing binoculars were critical because the conditions were already making spotting ice so hard. One failure amplified the next.
It's incredibly sobering and amazing how relevant these lessons still are over a century later.
Yeah.
You mentioned these tools, fishbone diagrams, 5 whys are still used.
Oh, absolutely. Aviation safety, medicine, software engineering, complex project management. Anywhere complex systems can fail, these ideas are vital.
Or preventing those same kinds of cascading failure.
Precisely. For digging into root causes, questioning assumptions, building in redundancy, learning from mistakes. The Titanic story, tragic as it is, offers incredibly valuable lessons for managing risk in almost any field.
It really makes you pause and think about any modern claims of something being too big to fail or, unsinkable, literally or metaphorically. What final thought should we leave our listeners with after this deep dive?
I'd just encourage everyone listening to take these ideas, this way of thinking, and maybe apply it to their own world, whether it's your work, your interests. Cultivate that habit of asking why.
Digging deeper.
Yeah, don't just accept the surface explanation. Challenge assumptions, especially the ones that seem completely solid, completely certain. Look for those hidden connections, those potential fractures under the surface.
Because that's where the real risks often lie.
Exactly. Keep digging deeper and keep asking why.